Hello and welcome to my presentation about Coco. My name is Gigerl and today I will talk about the co-design and co-verification of mask software implementations on CPUs. So Coco tries to verify countermeasures against physical side-channel attacks. In such attacks, we have a certain device which has a specific asset, for example, a cryptographic key. Examples for this device could be a government ID, a passport, a SIM card, or even a microprocessor which executes a cryptographic software which processes a secret cryptographic key. And then there is the attacker, and he has physical access to the device. This means that the attacker can manipulate and observe certain properties of the device. For example, it allows to observe or monitor the power consumption of a certain CPU while it executes a cryptographic algorithm. And then the power consumption depends on two things. First of all, which instructions are executed, and second, which data is involved. For example, the instructions could be whatever we need to do the AES, and the data could be the secret key, which is being processed by the AES. And in order to construct the countermeasure against that, we have to break this dependency. We can do that by applying a technique called masking. What we do essentially there is that we have our sensitive value, and we split it into multiple random shares. And then we don't do the computation on the sensitive value, but on the shares itself. For example, here we see that we can, for example, split the key K for a masked AES into 3 parts. And then if we observe the power consumption, each part will depend on a share individually. And if this share is random, then we have dependency on random data and not on the sensitive value anymore. This is not an easy task, which is why we need verification techniques to check if the shares are separated in a software or hardware. And the verification of such masking schemes is either done on algorithmic level or in a hardware circuit. And existing approaches have certain limitations. First of all, they have either focused purely on hardware circuits. An example would be the Rebecca tool, or purely on software. And those techniques dealing with software completely excluded the hardware, which is in the end used to execute the software. So the CPU netlist or the CPU itself was not considered, and it was assumed that it cannot cause problems. But this assumption is not true in practice. So what we want to do with Coco is that we verify for a specific software and a specific hardware that the execution of the software on the hardware is secure. And this we call co-verification. And we do that in two basic steps. First of all, we try to detect leakage of a given software execution on the hardware on netlist level. And second, we try to fix and identify certain pieces of the hardware which cause leakage, which is not that easy to see for the person writing the masked software. But how can hardware now exactly be a problem to mask software? Assume that there is an attacker, and the attacker probes or observes a specific wire in the CPU for exactly 1 clock cycle. The attacker will see all the signal fluctuations of this wire until the signal finally stabilizes. This includes transitions, so the change of the signal value from the old to the new value, but also glitches. A glitch occurs because there are variations in the propagation delay in combinatorial logic. And this is again caused by physical hardware properties, for example, different wire lengths or gate delays. For example, here we see the original Ibex register file, and assume we want to first read x2 and then x3. So in the first cycle, this multiplexer here will output x2, and also the final read port will output x2. The next cycle, we want to read x3. So this multiplexer will then switch to x1 because of the address bit. And then we have a transition from x2 to x1 on this wire. And if x2 and x1 are shares, we have a transition from one share to another. And we actually have a leak in our design. And the same thing happens for the write data. Also, these read addresses can glitch, which is even harder to make sure when writing software that it does not occur. But now let's have a closer look at the verification flow of Coco. So we start with our software and hardware, and the first thing we do is simulate the software execution on the hardware. Then we do the annotation, which means we tell the verifier which registers and memory locations contain our shares. And then we put that into the verification process, which either says, yes, the execution is secure, or no, it's not secure. And the leak is in this cycle at this gate. And the verification technique of Coco was inspired by Rebecca. Rebecca does pure hardware verification, and now with Coco, we extended that such that we can also verify software on hardware over multiple cycles. Coco can then further be used to perform what we call co-design. And co-design can be done for essentially any processor as long as you have the netlist. In our paper, we execute a case study using the RISC-V Ibex core. This is a very small core, 32-bit core with only 2 pipeline stages. But this core has, I would say, all the important component every other microprocessor has, for example, a register file or an ALU. And when we then ran our mask software on the Ibex core with Coco, we could identify leaks in the register file, in the ALU, in the data memory, and in the load store unit. And then we tried to find ways which allow us to still execute mask software without leaks. And for that, we need first hardware fixes, so changes in the CPU itself, and also software constraints, so rules our mask software has to follow. Here we can see how we hardened the Ibex register file in the end. So as you can see, we replaced the glitchy read address signal by an address signal originating from a register. And we did that by encoding the read address into a one-hot vector and storing it in the register. So everything which comes out of this one-hot register will not have glitches because it does not come out of combinatorial logic. And we can then use that bit to gate the register output. And therefore, we can make sure that we cannot have the same problem as we already talked about before. So the address signals are not glitchy anymore. And whenever we want to read, for example, x1, we will really only read x1. And we would not have any transitions from one register to another as long as we don't read these registers consecutively. So this would be an example of a rule which you would have for a software. We evaluated our approach, first of all, in terms of area, where we came to the conclusion that the area overhead of the core, excluding the SRAM, is about 10%. And then we tried to come up with some test cases which show that our verifier is also efficient. Here we have focused on S-boxes and masked multipliers, because when you construct a masked implementation, this is the hard part. And this is where leaks are very likely. So here we can see, for example, a Trajena end gate, also a DOM end gate. In this case, we have a broken DOM end implementation, so we can also find errors. And it reports the leaking cycle 12. But we also have some bigger test cases like the AES box, where we verified 1,900 cycles in 5 hours. And we also tried it with higher order tests, for example, the Hadzic S-box and masked third order DOM multiplier. Yeah, so this leads me to the end of my presentation. So with Coco, we tried to close the hardware-software gap. So existing tools only focused on masked software and did not consider the hardware. With Coco, we tried to co-verify software and hardware. And also we do co-design, which means that we find leaks in the CPU netlist by applying co-verification. And we have talked about how we verified and analyzed the RISC-V Ibex core and found leakages in that core. So this is the end of my presentation. Thank you for your attention, and if you have any questions, I'm very happy to answer them.